Good day and welcome to One-on-One Maths Private Tutors. Today we are looking at O-Level and IGCSE Computer Science. The topic is Methods of Error Detection. When data is transmitted, there is always a risk that it may be corrupted, lost, or even gained. Errors can occur during data transmission due to interference. All types of cables can suffer from electrical interference, which can cause data to be corrupted or even lost. Problems during packet switching can also lead to data loss or even data gain. Errors can also occur due to skewing of data. This occurs during parallel data transmission and can cause data corruption if the bits arrive out of synchronization. Checking for errors is important since computers are unable to understand text. For example, if the words are not recognized by its built-in dictionary. Let's look at the following example of some corrupted text. Can you read this? So we can see in this text, the words are corrupted. Whilst you probably had little problem understanding this text, a computer would be unable to make any sense of it. Data corruption is therefore a very real problem to a computer. The text here could be the result of some data corruption following transmission, which would make the text unintelligible to a computer. This is why error checking is such an important part of computer technology. The following section considers a number of ways that can be used to check for errors so that you do not end up with text as shown here. There are a number of ways data can be checked for errors following transmission. The first one is parity checks. The second one is checksum. The third one is echo check. Parity checking is one method used to check whether data has been changed or corrupted following or after data transmission. This method is based on the number of 1 bits in a byte of data. The parity can either be called even, that is an even number of 1 bits in the byte, or odd, that is an odd number of 1 bits in the byte. One of the bits in the byte, usually the most significant bit or the leftmost bit, is reserved for a parity bit. The parity bit is set according to whether the parity being used is even or odd. For example, consider this byte. In this example, if the byte is using even parity, then the parity bit needs to be set to 0, since there is already an even number of 1 bits in the byte. So we have 1, 2, 3, 4 bits. So if we are using even parity, we already have an even number of bits. So we'll set the most significant bit or the leftmost bit here to 0. So what we want is to have an even number of ones in this byte. In this example below, if the byte is using odd parity, then the parity bit, which is our leftmost bit, needs to be set to 1, since we need to have an odd number of 1 bits in the byte. So in our byte, we had 1, 2, 3, 4. So if we are using odd parity, we want to make the number of 1 bits odd in our byte. So the parity bit or the leftmost bit will be set to 1 so that we have 1, 2, 3, 4, 5, which is an odd number of 1 bit in this byte. Before data is transferred, an agreement is made between the sending device and the receiving device regarding which type of parity is to be used. Parity checks are therefore being used as a type of transmission protocol. Now let's look at this question. Find the parity bits for each of the following bytes. So we want the bit that will go there, whether it will be a 0 or a 1. Here we are using even parity. So we want an even number of 1 bits. So we have 1, 2, 3, 4, 5. So here we have to add a 1 to make it even. So we'll have 6 bits. Even parity on this one, 1, 2, 3, 4. We have an even number of ones already, so here we'll add a 0. Even parity is being used on this one, so we have 1, 2, 3. To make it even, we put a 1 there, so we have 4, which is an even number of 1 bits. Odd parity is being used on this one, so we have 1, 2, 3, 4. So we must put 1 to make it 5, so that the number of 1 bits is odd. Odd parity is used here, so we must have an odd number of ones. So we have 1, 2, 3, 4, 5. Already odd, so we put 0 there. Even parity is being used. We have 1, 2, 3, 4, 5, 6, which is already even, so we put a 0 here to maintain the number of ones as even. Odd parity is being used here, so we have 1, 2, 3, 4, 5, 6. We must put a 1 there to make it 7, which is an odd number. Odd parity is being used here, so we have 1, 2, 3, which is already odd, so we put a 0 there. Even parity is used here, so we must have an even number of ones. So we have 1, 2, 3. So we have to add 1 there to make the number of ones even. Odd parity is used here. So we have 1, 2, 3, 4, 5, 6, 7, which is an odd number. So we must put 0 there to maintain the odd number of bits. So that's how we use parity bits on the most significant column. If a byte has been transmitted from A to B, and if even parity is used, an error would be flagged if the byte now had an odd number of 1 bits at the receiver's end. For example, assuming that we are using even parity here, if the byte being sent has 1, 2, 3, 4, which is an even number of ones, and when it is received, it has 1, 2, 3, then we know an error has occurred since this bit has changed from a 1 to a 0. In this case, the byte received has 3 1 bits, which means it now has odd parity, while the sender's byte was using even parity, which was 4 1 bits. This means an error has occurred during transmission of the byte. The error is detected by the receiving computer recalculating the parity of the byte sent. If even parity had been agreed between sender and receiver, then a change in parity in the received byte indicates that a transmission error has occurred. Now let's look at this question. Which of the following received bytes indicate an error has occurred following data transmission? If even parity is being used here, then we should have an even number of 1 bits. So here we have 1, 2, 3, 4, 5, 6. So it's likely that there is no error. Here the even parity is used, so we must have an even number of ones. Here we have 1, 2, 3, 4, 5. These are not an even number of ones. Even numbers are 2, 4, 6, 8, 10, 12. So if even parity is used and we find 1, 2, 3, 4, 5, then an error has definitely occurred. If even parity is used here and we have 1, 2, 3, 1 bits, then definitely an error has occurred. If odd parity is being used and we have 1, 2, 3, 4, 5, it's most likely that there is no error. If odd parity is being used here and we have 1, 2, 3, 4, 5, 6, it definitely means that there is an error. If odd parity is used here and we have 1, 2, 3, 4, 5, 6, 7, 8, then it means we have an error because the number of ones we should find are 1, 3, 5, 7, 9, 11, and so forth, odd numbers. So in odd parity, we should have odd numbers of 1 bits, and in even parity, we should have even number of 1 bits. However, if 2 of the bits change value following data transmission, it may be impossible to locate the error using parity checking. Let us imagine that we are transmitting the following byte using even parity. So we have 1, 2, 3, 4, which is correct in even parity. Suppose more than 1 bit has been modified or changed during data transmission. This means the byte could have reached the destination as any of the following. So we can have this bit changing and that bit changing, and still we have 1, 2, 3, 4, 5, 6, which is correct in even parity. Or we can have these 2 bits changing into zeros and we have 1, 2, which would be correct in even parity. Or we can have these 2 bits changing or flipping, and this one becomes a 0 from a 1, and this one becomes a 1 from a 0. Still, we have 1, 2, 3, 4, which is correct in even parity. In all these cases, the byte has clearly been corrupted, but the bytes have retained even parity. Therefore, no error would be flagged in spite of the obvious errors in the transmission. Clearly, it would be necessary to have other ways to complement parity when it comes to error checking to ensure errors are never missed. One such method is called checksum. So with parity, even though an error is detected, it is impossible to know exactly which bit is in error. One of the ways around this problem is to use parity blocks. In this method, a block of data is sent and then the number of 1 bits are totaled horizontally and vertically. In other words, a parity check is done in both horizontal and vertical directions. This method not only identifies that an error has occurred, but also indicates where the error is. In this example, 9 bytes of data have been transmitted. Agreement has been made that even parity will be used. Another byte, known as the parity byte, has also been sent. This byte consists entirely of the parity bits produced by the vertical parity check. The parity byte also indicates the end of the block of data. The table below shows how the data arrived at the receiving end. It is now necessary to check parity of each byte horizontally, bytes 1 to 9, and vertically, columns 1 to 8. Each row and column where the parity has changed from even to odd should be flagged. So we have our bytes 1 to 8. So this is our first byte, and this is our parity bit for that byte. So we have 1, 2, 3, 4, 5, 1 bits. And since we are using even parity, we will have to add this parity bit as a 1 to make them 1, 2, 3, 4, 5, 6 bits, which are even. Our second byte is this byte, our 7-bit byte. It has 1, 2, 3, 1 bits, which are odd. Since we are using even parity, we had to add this 1 to make sure that they are even. Our third byte is this byte there, which has 1, 2, 3, 4, 5, 6, an even number of bits. That is why we put a 0 there. Our fourth byte is this byte here, which has 1 bit. So we have to add a 1 there to make them even, since we are using even parity. So our parity bit will be a 1. Our fifth byte is this byte here, which has 1, 2, 3, 4, 1 bits. So they are already even, so we have a 0 there. Our sixth byte is this byte here, which has 1 bit here. So we had to add a 1 to make them 2, so that we have an even number of bits. Our seventh byte is this byte here, which has 1, 2, 3, 4, 5, which is why we had to put a 1 here to make them 6, so that it has even parity. Our eighth byte here is this byte, which has 1, 2, 3. But here there is a 0, which means the error is on this byte, which is why it has been highlighted, because it's not following even parity. Our ninth byte is here. We have 1, 2 bits, which are even, and that's why there's a 0 here to maintain an even number of 1 bits. Now, for the horizontals, we have identified the error is here. But this is a parity block. So we also do a parity check in the vertical. Now, this allows us to pinpoint where the error has occurred. So for this first column, we have 1, 2, 3, 1 bits. So we will add a 1 to make them 4, which will make it an even parity. For our third column, we have 1, 2, 3, 4, which are already even. So we put a 0 there. For our column 3, we have 1, 2, 3, 4, 5, which is odd, and we put a 1 to make it even. For our column 4, we have 1, 2, 3, 4, 5, and there is an error because we have 0 instead of a 1 to make them 6. So this row and this column, there is a problem, and we have identified the bit that should be flipped. This should be a 0, so that we have 1, 2, 3, 4, and this would be a 0. On this row, 1, 2, which are even, and this one becomes a 0. Now, if we check the rest, we will see they concur or they go along with even parity. Our parity bits can also be checked, because this is 1, 2, 3, 4, 5, and we put a 1 to make it 6. And our parity bits here are 1, 2, 3, and we put a 1 there to make it 4. So if we use parity blocks, then we have a way of identifying where the error occurred. A careful study of the table shows the following. Byte 8, row 8, which is byte 8, has an incorrect parity. As we have seen, there are 3 1 bits. Bit 5, which is this one, column 5, also has an incorrect parity. There are 5 1 bits, 1, 2, 3, 4, 5, which affects here. Secondly, at the intersection of row 8, column 5, the position of the incorrect bit value, which caused the error, can be found. The 1 bit at this intersection should be a 0 bit, as we have corrected here. This byte could therefore be corrected automatically as shown above, or an error message could be relayed back to the sender asking them to retransmit or resend the block of data again. Now let's look at this question. The following block of data was received after transmission from a remote computer. Odd parity was being used, so we are using odd parity by both sender and receiver. One of the bits has been changed during transmission stage. Locate where this error is and suggest a correct byte value. So let's look at this row. Our first byte is this byte here. We have 1, 2, 3. This is in agreement with odd parity, so there's a 0 there. Here there's 1, 2, 3, 4, 5, 6. So our parity bit should be 1. On this row, we have 1, 2, 3. So this is in agreement with odd parity. Here we have 1, 2, 3, 4. These are even. So this row is in error. Now we were told that 1 bit was changed. So now we start looking at this vertical column. 1, 2, 3, 4, 5. This is in agreement with odd parity. 1, 2, 3, 4, 5. This is in agreement with odd parity. 1, 2, 3, 4, 5, 6, 7. This is in agreement with odd parity. 1, 2, 3, 4, 5. This is in agreement with odd parity. 1, 2, 3, 4, 5. Also in agreement with odd parity. 1, 2, 3, 4. Here we have the problem. Since we have 1, 2, 3, 4, 1 bits which are even. So this one has to change into a 1. So we can say byte 4 should be 0, 1, 1, 0, 1, 1, 1, 0. This should be our suggested byte. Thank you.